Okay, so here's an example to help you study for the final exam of using a TS diagram, which is a temperature salinity diagram, to determine the character of a new water sample if you mix 2 or 3 different water samples together. Okay, so we're going to go ahead and get started with the example. Here is sort of the basic layout that we're going to see as we move through this example. Over here on the left, in this region, we're going to find each step as we move along. Up here in the top region, all right, is always going to be the 3 different samples and the characteristics of those 3 samples. In this blank area over here on the right currently, where there's nothing, we're going to find more detailed instructions for each step as we go. Okay, so let's get started with this particular example. The very first step is to plot the samples on the TS diagram. So in this case, we have 3 different samples that need to get plotted on our TS diagram. Sample 1, which I've plotted in red, is seen here at 20 parts per thousand and 16 degrees Celsius. Sample 2 is seen here with 35 parts per thousand and 37 degrees Celsius plotted in blue, and in green is sample 3 at 40 parts per thousand and 10 degrees Celsius. Now, if you want to try to do this on your own as we go along, you can do so and then check your answers as you go. You can just use the TS diagram that's in your lab manual. So the second step is to determine the scale for interpolation to be able to determine the densities of each of our samples. We'll also use this scale later after we've done the mixing exercise to determine the density of those samples. So here's the deal. None of our 3 samples, the red, the blue, or the green, falls exactly on one of the lines of equal density. So we have to interpolate to be able to give a quantitative estimate as to what the density is of those materials. Okay, so let's start with the first aspect. We need to measure the distance between 2 of these lines. All right, so in this case, according to our ruler, it is 1.2 centimeters between those 2 lines. So that's what I've written over here on the right. 1.2 centimeters on the paper represents the difference in density between those 2 lines, which are 13.3 sigma t and, doesn't matter, 11 or 15.6 sigma t. And so that it means that 1.2 centimeters on the paper represents 2.3 sigma t in our density scale. So that completes our interpolation calculation. So now we can use that to figure out the densities of samples 1, 2, and 3. Okay, so step 3 is to actually interpolate the densities of each of the samples 1, 2, and 3. So I'll walk you through the details on sample 1, and then we will just go ahead and use the next couple of slides to go through sample 2 and sample 3. But I'll let you follow along on those on your own. So the very first step is that we're going to use that 1.2 centimeters over 2.3 sigma t, and we're going to set that equal to the distance our sample is from one of those density lines. So in this case, if we zoom in to the red sample, sample 1, we see that it is 0.5 centimeters away from the 13.3 line. And so we can say that 1.2 centimeters on the paper represents 2.3 sigma t in the real world, and we can set that equal to 0.5 centimeters on the paper, and we're going to solve for x. What does that mean in the real world? And what that's going to tell us is how many sigma t we are away from 13.3. So we can solve for x, and we find through cross multiplication that x is equal to 0.96 sigma t. Now that just tells us that we're 0.96 sigma t away from 13.3. So we can add those together, and our density for sample 1 is then 14.26 sigma t. We'll do the exact same thing for sample 2 and sample 3 on the next 2 slides. So since we've now calculated the density for sample 1, sample 2, and sample 3, they're written at the top in that table, we're going to then actually do the mixing problem now. If our problem is that we're going to mix equal amounts of sample 1 and sample 2, let's say 100 milliliters of each, we want to know what the temperature, the salinity, and the density will be of that new solution, which is 200 milliliters, half of it sample 1 and half of it sample 2, mixed well together. So the very first step is that we want to draw a line between our two samples. We know that if we mix sample 1 and sample 2 in whatever proportions, the final mixture must fall on this line. This is called a mixing line. We can use this to graphically help us figure out what the resulting water will look like. Once we have our line, and we know that we're mixing equal amounts of both water types, sample 1 and sample 2, we know that our new mixture will be exactly halfway along that water line. So in this example, I measured along the line. It came out to be 10.4 centimeters. I moved the ruler to be able to do that. And so our new water, where the black square is 5.2 centimeters along that line. That's exactly halfway. Once again, that line does not fall right on one of the lines of equal density. So we need to interpolate what the density will be. In this case, because we mixed half and half of the exact same sample, we can actually calculate the temperature and salinity very simply. And that is by just taking the average of the two. Temperatures and salinities can be used this way. However, density must be interpolated from the diagram. So I took the average of salinity and temperature, and they're shown there on the right. And then with density, once again, I used my ruler. I measured how far it was away from this particular line of equal density. And then from there, I figured out that it was 0.8 centimeters away from the 15.6 sigma T line. I solved again for what that would represent, that 0.8 in sigma T, added it to 15.6, and got a density of 17.44 sigma T. I can double check to make sure that that looks to be about right by seeing where it falls in between these two lines. It must be between 15.6 and 17.9, and 17.44 looks like a good estimate. Okay, so now I have a brand new sample, this black box sample. And the next step, what we're going to do is we're going to mix in our third type of water. Once again, 100 milliliters of this. So to get us started, once again, we're going to draw a mixing line between sample 3, the green dot, and the sample that was created by the mixture of 1 and 2. Now, in this case, we're mixing 200 milliliters of the black box sample and only 100 milliliters of the green sample number 3. Therefore, the resulting sample, all right, has to be similar, more similar to the black box sample than it is to the green sample. And it turns out, if we do the math, 100 milliliters of sample 3 added creates a total of 300. So we can just take 100 divided by 300 and we get 1/3. So we know we have to measure 1/3 of the way along the line. So once again, we get out the ruler, we measure the entire length of the line, which in this case is 8.5 centimeters. If we take that 8.5 centimeters and we divide it by 3, because we're looking for 1/3, we end up with 2.8 centimeters. And so we place the new dot to locate where the newest mixed sample would be. It's going to be 2.8 centimeters away from the water that has the most in it, which is 200 milliliters of this black box mixing sample. And so our new solution with 100 milliliters of sample 1, our 100 milliliters of sample 2, and 100 milliliters of sample 3 can be found right here in this location. To calculate the final salinities and temperatures and densities, we need to read right off the graph. For the salinity and the temperature, we can read right off the graph. And so, as we see here, we've got a temperature sitting at a little bit above 20. I would say it's about 21 degrees Celsius. And we can find this line here, which turns out to be about 31.5 parts per thousand. And then with density, once again, we zoom in, we measure the distance from the smallest sigma T line. We then plug that into our relationship 0.9 centimeters, and we're solving for this X. And so we find out that if we do that and we follow the same instructions as we've done the last few times, we come up with a density of 21.93 sigma T. We double check again to make sure that that seems legitimate between 20.2 and 22.5, and that does seem like a good number. And so we've calculated the final temperature, salinity, and density for a sample indicated by the yellow box, which is equal parts sample 1, sample 2, and sample 3. You can now go back if you want to and pause your way through and rewatch this video if you want to take it a little bit more slowly and step by step.